In this lecture, we'll talk about solving systems of linear equations using matrices. First, we should talk about what a matrix is. So a matrix is defined to be a rectangular array of numbers. For example, we have a matrix here. The horizontal parts of the matrix are called rows, and the vertical parts of the matrix are called columns. So each entry in the matrix can be identified by its position in the matrix. For instance, in the upper left-hand corner, we have A sub 1, 1. The first one says that that entry is in the first row, and the second one says it's in the first column. So if we look down towards the middle of the matrix, we have entry A sub ij. That's the entry that's in the ith row and the jth column. We have a special matrix that's related to a system of equations that's called the augmented matrix of the system. So basically, we can rewrite a system of equations using a matrix, and when we do this, the following are going to be true. First, the rows of the matrix will correspond to the equations in the system. So the first row represents the first equation, the second row represents the second equation, and so on. Next, the columns of the matrix will correspond to the different variables and constants in the system. Typically, the first column goes with the first variable, which is often x. The second column will go with the second variable, which is often y, and so on. The vertical line in our augmented matrix represents the equal sign. The numbers that are present in the matrix are the coefficients of the system, so we won't see any x's or y's in the matrix, just their coefficients. And a matrix that has m rows and n columns is said to be of order m by n. So let's look at a couple of examples. We want to find the augmented matrices for the following systems. First, we have 3x plus 4y equals 7 and 4x minus 2y equals 5. This is a system of two equations, so our matrix should have two rows, and we have variables x and y and the constants 7 and 5, so we should have three columns, one to represent x, one to represent y, and one to represent the constants. So if we copy over the coefficients, we'll see that the augmented matrix is the one with the first row being 3, 4, and 7, and the second row being 4, negative 2, 5. We place the vertical bar in between the 4, 7, and negative 2, 5, because that's where the equal signs are. And remember, when we look at this, the first column represents our x coefficients, the second the y coefficients, and on the other side of the vertical line are our constants. Let's try to find the augmented matrix for the system 5x minus y minus z equals 0, x plus y equals 5, and 2x minus 3z equals 2. So this problem has three equations, which means our matrix should have three rows. We have variables x, y, and z plus constants, so we should have four columns. Take a minute or two and see if you can figure out what the augmented matrix looks like. So again, just copying over the coefficients, where the first row represents the first equation, the second row represents the second equation, and the third row represents the third equation, and the first column represents our x's, second column our y's, third column our z's, and the fourth column the constants on the other side of the equal sign, our augmented matrix will look like this. We should be able to go backwards as well, so we should be able to find the system of equations if we're given an augmented matrix. So let's consider the matrix with the first row being 1, negative 3, 3, negative 5, the second row being negative 4, negative 5, negative 3, negative 5, and the third row being negative 3, negative 2, 4, and 6. We want to take this matrix and use it to write a system of equations. So again, the rows represent the different equations. The first column will be our x coefficients, the second column will be our y coefficients, the third column will be our z coefficients, and the column on the other side of the vertical line will be our constants, with the vertical line being the equal sign. If we put all of that together, we get the system of equations x minus 3y plus 3z equals negative 5, negative 4x minus 5y minus 3z equals negative 5, and negative 3x minus 2y plus 4z equals 6. There's a special form of the matrix that we're going to try to achieve that's called Rowechelon form. Once you get a matrix in Rowechelon form, you've basically solved for one variable of the system and can use back substitution to find the other variables. A matrix that's in Rowechelon form will have ones along the diagonal, and a matrix that's in Rowechelon form will have zeros below each one on the diagonal. So here's an example of a generic matrix that's in Rowechelon form. Notice we have ones along the diagonal and zeros beneath each one on the diagonal. Once we have a system written in matrix form, we can use row equivalent operations to transform the matrix to get it into Rowechelon form. So we can do the following operations on a matrix without changing the system that it represents. First, we can interchange any two rows. So we could take row 1 and swap it with row 3, or take row 2 and swap it with row 1, and that does not change our system. Second, we can multiply each entry in a row by the same non-zero constant. This is the operation that we'll use to get the ones for Rowechelon form. And finally, we can add a non-zero multiple of one row to another row, and this is the operation that we'll use to get the zeros when we're trying to find Rowechelon form. So let's look at a couple of examples where we deal with row operations. We're given the matrix 1, -3, 3, -5, 4, -5, -3, -5, and -3, -2, 4, and 6. And we want to perform the following row operations. First, replace row 2 with 4 times row 1 plus row 2. Second, replace row 3 with 3 times row 1 plus row 3. So let's start with replacing R2 with 4 times row 1 plus row 2. In order to conduct this row operation, we'll multiply each element of row 1 by 4. So that will transform the first row, 1, -3, 3, -5, to be 4, -12, 12, and -20. And then the second row will stay the same, -4, -5, -3, -5. We're going to add these two rows together, and that results in a new row, 0, -17, 9, -25. So to complete this row operation, we'll replace row 2 in our matrix with this new row. The second part of our example says replace row 3 with 3 times R1, so 3 times row 1, plus our original row 3. So to begin with, we're going to multiply row 1 by 3, so that'll give us 3, -9, 9, and -15. And we're going to add row 3, -3, -2, 4, and 6. We'll add these rows together term by term, and that'll give us the new row 0, -11, 13, -9. To complete the row operation, we'll replace the third row with the new row. So our new matrix looks like this. So let's do an example where we're going to use row operations to solve a system of equations. We have the system x plus 2y equals 5 and x plus y equals 3. The first thing that we're going to want to do is find the corresponding augmented matrix of our system. So that'll be this matrix with rows 1, 2, 5 and 1, 1, 3. Now we want to manipulate this matrix to get it in Rowechelon form. To start with, we want to get a 1 in the upper left-hand corner, so the first row, first column. And we already have that, so we can move on. We want to make everything below that 1 a 0. So if we look at -R1 plus R2, for the first column that's -1 plus 1, that gives us 0, so we'll put 0 in the first column. -2 plus 1 gives us -1, so we'll put -1 in the second column. And -5 plus 3 gives us a -2, so we'll put a -2 in the third column. So now we have the 0 in the position that we wanted. The next thing we want to do to put this in Rowechelon form is transform the -1 that's in the second row, second column, into a +1. So to do this, we'll replace row 2 with row 2 divided by -1. If we divide each term in row 2 by -1, we'll replace it with 0, 1, 2. Now we have a matrix that's in Rowechelon form. So we can transform the matrix from the Rowechelon form back into the system of equations. The corresponding system of equations is x plus 2y equals 5. and y equals 2. And since we know that y equals 2, we can take that value and plug it into the first equation to give us x plus 2 times 2 equals 5. So x plus 4 equals 5. If we subtract 4 from both sides, we'll get x equals 1. So now we know x equals 1 and y equals 2. So the solution to this system is the ordered pair 1, 2. And we can plug this back into the system to check our answer. Let's look at another example. So this time we're going to have a system of 3 equations with 3 unknown variables. We have 2x minus y plus 4z equals negative 3, x minus 2y minus 10z equals negative 6, and 3x plus 4z equals 7. The first thing that we want to do is transform this system of equations to its corresponding augmented matrix. So again, the first row of the matrix represents the first equation. The second row will give us the second equation, and the third row comes from the third equation, with the first column being the x coefficients, the second column being the y coefficients, the third column being the z coefficients, and the fourth column on the other side of the vertical line being our constants. So this is our augmented matrix. Now, to solve the system of equations, we want to put this in Rowechelon form. So we want the first entry in the first row, first column, to be a 1. And there are a couple of ways that we can accomplish that, getting a 1 in the first row, first column. But the easiest one is just to switch rows. So let's switch row 1 and row 2. If we switch row 1 and row 2, our matrix now looks like this. So we have 1, negative 2, negative 2, negative 6, 2, negative 1, 4, negative 3, and 3, 0, 4, 7. The next thing we want to do to get this in Rowechelon form is to get the 2 underneath the 1 in the first column to be a 0. So in order to do that, we'll multiply row 1 by a negative 2, and then add the 2 rows together. So we're going to replace row 2 with negative 2 times row 1 plus row 2. So let's look at this column by column. If we take negative 2 times 1 and add 2 to it, that'll give us a 0. Negative 2 times negative 2 gives us a positive 4, and positive 4 plus negative 1 gives us 3. Negative 2 times negative 10 gives us a positive 20. 20 plus 4 gives us 24. And negative 2 times negative 6 gives us a positive 12. Positive 12 minus 3 gives us 9. So our new row is 0, 3, 24, 9. Next, we want to get the 3 at the bottom of the first column to be a 0 as well. So we can use the same approach. We'll replace row 3 with negative 3 times row 1 plus row 3. So again, if we look at that column by column, for the first column, if I multiply negative 3 times 1, that's negative 3, and negative 3 plus 3 is 0. If I multiply negative 3 times negative 2 in the second column, that's a positive 6. 6 plus 0 is 6. If I multiply negative 3 times negative 10 in the third column, that's a positive 30. 30 plus 4 is 34. And if I multiply negative 3 times negative 6 in the fourth column, that's a positive 18. And 18 plus 7 is 25. So our new row 3 is 0, 6, 34, 25. Okay, so the next thing we want to do to get things in Rowechelon form is replace the 3 in the second row and the second column with a 1. We can accomplish this by multiplying the entire second row by 1/3. So we'll replace row 2 with 1/3 times row 2. So if we multiply the entire row by 1/3, 1/3 times 0 gives us 0, 1/3 times 3 gives us 1, 1/3 times 24 gives us 8, and 1/3 times 9 gives us 3. So our new row is 0, 1, 8, 3. The next thing that we want to do to get this in Rowechelon form is transform that 6 in the second column, third row, into a 0. And we should be able to accomplish that by multiplying row 2 by negative 6 and adding it to row 3. So if we conduct that row operation, negative 6 times row 2 plus row 3, term by term, for the first column we get negative 6 times 0 plus 0 gives us another 0. For the second column we get negative 6 times 1, which is negative 6, and we add 6 to it, that gives us another 0. For the third column we get negative 6 times 8, that's a negative 48, and negative 48 plus 34 gives us negative 14. And finally, for the fourth column, we take negative 6 times 3, that's a negative 18, and we add negative 18 plus 25, that gives us a 7. So our new third row is 0, 0, negative 14, 7. Now the last thing that we need to do to get this in row echelon form is replace the negative 14 in the third row, third column, with a 1. This can be accomplished using the row transformation. Row 3 equals negative 1 over 14 times row 3. If we apply the new row operation, multiplying row 3 by negative 1 over 14, we'll get a 0 and a 0 for the first two entries. Negative 1/14 times negative 14 gives us 1, and negative 1/14 times 7 gives us negative 1/2. So our new row is 0, 0, 1, negative 1/2. Now that our matrix is in row echelon form, we can convert it back to a system of equations and use back substitution to solve the problem. So this matrix in row echelon form corresponds to the system of equations: x minus 2y minus 10z equals negative 6, y plus 8z equals 3, and z equals negative 1/2. So we know that z is equal to negative 1/2. We can take that value and plug it into the equation above to find out what y is. That'll give us y plus 8 times negative 1/2 equals 3. If we simplify, that gives us y minus 4 equals 3. And if we add 4 to both sides of the equation, we get y equals 7. Now we know that y equals 7 and z equals negative 1/2, so we can plug those into the first equation to solve for x. So we'll get x minus 2 times 7 minus 10 times a negative 1/2 equals negative 6. If we simplify the multiplication, that'll give us x minus 14 plus 5 equals negative 6. And if we simplify, we'll solve and get x equals 3. So the solution to this system of equations is the ordered triple 3, 7, negative 1/2. There's another special form of the matrix that we could use. It's called reduced row echelon form. So to put a matrix in reduced row echelon form, we'll first need to find row echelon form. And instead of stopping when we get into row echelon form, we're going to continue using row operations until we have 1s on the diagonal and 0s everywhere else. So a matrix that corresponds to a 3 by 3 system would look like this when it's in reduced row echelon form. Notice it has 1s on the diagonals and 0s everywhere else. And once you have your matrix in row echelon form, there's really nothing else to solve. When you transform that back to the system of equations, you'll get x equals a, y equals b, and z equals c. So let's look at an example dealing with reduced row echelon forms. The reduced row echelon form of a system of linear equations is given. Write the system of equations corresponding to the given matrix, determine whether the system is consistent or inconsistent, and if it is consistent, give the solution. So our reduced row echelon matrix takes the form 1, 0, 4, and 0, 1, negative 1. If we transform this into a system of equations, we'll get x equals 4 and y equals negative 1. Since x and y both have distinct values and there are no inconsistencies, this system is a consistent system, and the solution to the system is the ordered pair 4, negative 1. So let's look at another example. Again, the reduced row echelon form of the system is given. We want to write the system of equations that corresponds to the matrix and determine whether the system is consistent or inconsistent. And if it's consistent, we'll give the solution. This time our matrix looks like this: 1, 0, 0, 7, 0, 1, 0, 2, and 0, 0, 0, 3. If we transform the matrix back over to equations, we'll get x equals 7, y equals 2, and 0 equals 3. But we have some inconsistencies here. 0 does not equal 3, so this system is inconsistent, meaning there's going to be no solution. Here's one last example. Again, the reduced row echelon form of the system is given. We want to write the system of equations that corresponds to the matrix and determine whether the system is consistent or not. If it's consistent, we want to find the solution. This time our matrix is 1, 0, 7, negative 3, 0, 1, 8, 4, and 0, 0, 0, 0. If we transform this to a system of equations, we'll get x plus 7z equals negative 3, y plus 8z equals 4, and 0 equals 0. Now, since all of these work, this system will be consistent. However, we don't have a distinct value for x, y, and z. So we'll need to solve everything in terms of the same variable. So let's get everything in terms of z. If x plus 7z is equal to negative 3, I can solve this equation for x, giving me x equals negative 3 minus 7z. And if y plus 8z is equal to 4, we can solve this equation for y, giving us y equals 4 minus 8z. Now that we have both x and y in terms of z, we can write out the solution to the system all in terms of z. So we'll have an infinite number of solutions, and they'll take the form negative 3 minus 7z, 4 minus 8z, and z.